Okay, predict whether the molecules PF3 and PF5 are polar or non-polar. Predict means I don't expect you to know this. It's not a fact that I expect you to know. It's something that I expect you to be figuring out right now. Molecules PF3 and PF5, tell me about both of them, not just one of them, are polar or non-polar. Those are the only two answers I want. So PF3 is the first one. And PF3, it has got delta minus here and delta plus here. So it's going to, so the fluorine's going to be more electronegative than the phosphorus. So it's going to have a dipole. The dipole is going to be present, and you're also going to have a dipole here across this bond. The bonds are polar. The bonds in both of them are polar because you have got that electronegativity difference. The thing is that PF3 is not symmetrical. And because it's not symmetrical, that means that it remains polar, a polar molecule with polar bonds. Now, the difference is that if we have got PF5, PF5 is symmetrical. And because it is symmetrical, all of the dipoles across the bonds cancel out. And if all of the polar bonds cancel out, then we're left with something that is not polar. Or actually, should be saying non-polar. Now, I know that if you look at PF5, it doesn't look particularly symmetrical. What you have to try and think of is, if you were any of the fluorines on that molecule, would your view, would your environment be the same, or would it be different to the other fluorines on that molecule? So every single one of those fluorines has the exact same environment. Whatever it's looking at, however far away it is from something, every single fluorine is identical. So that molecule is symmetrical, even though I appreciate that when you look at it, you might not immediately see mathematically that it looks like it's symmetrical. So you can, I suppose, learn that if you have got the same atom on all of those bonds, so the P is bonded to 5 of the same atom, and you've got no lone pairs of electrons, then that is going to be symmetrical.